SyMRI is an MR quantification tool. We measure physical properties. So we measure really the R1 relaxation rate, R2 relaxation rate, and protein density. So rather than images, it's really a physical property that we have a number on. So we get maps, but to make you more at home with looking at these maps, we can always convert them to synthetic MRI. So it's kind of like a virtual scanner. You got the maps, you got physical properties, and you recreate the T1 weights, the T2 weights, and flares based upon them. So any combination of echo time, repetition time, inversion delay, you can just regenerate. You don't need the patient for that. So that's one part of it. The other part is quantitative tissue maps. So we have definitions of what is gray matter, white matter, myelin, etc. We also create these maps. Well, it's all based on the same sequence. It's a FDA cleared, CE marked, at least our multi-slice 2D solution. And we're available on Philips, on GE, on Siemens. Unfortunately, we have a bit different names, which might add to the confusion. But on Philips, it's called Syntac. On GE, it's presented as Magic. And on Siemens, it's MDME, but it's all SyMRI, yeah, and created by us. It's you, yeah. Screen is not great, but at least I can show you the idea behind it. 3D, obvious. We have this solution today. It's a multi-slice turbo-span echo-based sequence. So typically we have 4mm slices. And they have a high resolution in plane. So you have about 30 slices covering the head, but you're not able to make some sort of reformat. That'll be a very low resolution. Enter our 3D, a little lower resolution in plane, but now a much higher resolution out of plane. So typically we have 150 slices there. Oh, hi. Okay. And the scan time is the same. So originally it was about 6-7 minutes, but with the advent of the AI recon methods as air and smart speed, we can go down to about 4 minutes now. 4 minutes, full quantification. So maybe the next slide. Because that was all the synthetic imaging, so you can recreate the T1s, T2s, and anything you want. And on top of it, you can also recreate like CSF, the intracranial volume, as you see here in the red line, the myelin maps, everything. All in 3D. All right. So how do we do that? A little background on that sequence. It's called 3D CALAS. It has already been published 2014. It was applied on the heart first. And that was created to be ultimately fast. So we could get T1, T2 PD of the heart in single breath hold. But the concept is just the same. The only thing we do for the brain is just to scan longer and have a higher resolution. So what it does, if you follow the mechanization over time, it has T2 prep pulse to code for T2. It has an inversion to code for T1. And if you measure all the way and extrapolate to infinity, then you would get PD. We actually have a method to even infer the B1 field in this. And that saves us a lot of trouble because you need B1 to do a correct measurement of T1, T2, and PD. That's also part of the 2D solution, and we have transformed that to 3D. So this is what you get then, the maps. So this is R1, the R1 relaxation rate on a scale 0 to 2.5 per second. So that's the inverse of T1 relaxation, right? You can get it in all reformats. This is the R2 relaxation rate and protein density. And to make you appreciate that this is really high resolution, I made a zoom in of the R1 relaxation rate here in black and white. I mean, this is not faking with some nice colors and color scheme. This is a really truly high resolution. So 1.0 isotropic and in 4 minutes. Yeah. And what you can do with that is, well, multiple things. Of course, the synthetic images. So you get every image in one go, all the T1, T2, and flares. But moreover, you can characterize the tissue. So here on the synthetic flare, you can place regions of interest if you want, and look at edema, tumors, and can follow that over time or follow that throughout the patient. So we provide what we call Q plots, quantitative plots. So it's of course 3-dimensional. There's also PD here, but you can switch the view. It's R1 and R2. The typical positions of CSF, gray matter, and white matter are there. So that's the average adult position or coordinate in that space for gray matter, white matter, and CSF. And you can see in relation to that where your pathology or any tissue of interest is residing. Right. So that's one aspect of it. You can work on it locally. And if you have the next slide. But we also provide an automatic solution that can find the brain for you, the intracranial volume and the amount of myelin. And that's all summed up. And so you'll get a table. So here's a few examples where here's, for example, CSF, here's myelin. This is anything that we did not recognize, what we call none. But there's tooling in there that you can selectively select part of that none to see what kind of characteristics that has. This can all be plotted, and it is all summed up in a table. Oh, you had a question?
It's not sorry.
Yeah, it's not CSF, it's not white matter, it's not gray matter. So we have definitions of what we consider as healthy or normal white matter, gray matter, and CSF. That's based on our regional interest placement of a number of radiologists. And that gives you a sort of statistical distribution within that R1, R2 PD space. So anything that falls outside that will end up in this, non-thing. That could be blood, like all vessels in there. It could be some artifacts, but it also contains pathologies. So it's a-specific. You shouldn't really use it, but at least it's kind of like a messenger that something is going on there. It's beyond what is considered to be normal. All right. I'll get back to that. So these are the sums. So this patient has a brain volume of 1103 milliliters. It's an intracranial volume so much. We usually take the ratio of that, the BPF, brain parenchymal fraction. And this is a very good number to monitor over time, considering the ICV is stable. We have a repeatability error of 0.2%. So for us, it's stable. And then actually, now that with the FDA, it was kind of interesting. Of course, we have repeatability measurements, but so we scanned a couple of our personnel again, but they failed our repeatability requirements because their brains got too small. They were smaller than the 0.2%, but that's actually what happened. It was for real because, that's what happens if you get a little older. There was a 3 year in between, and 3 years is on normal atrophy of the brain is so much that it falls outside of our repeatability requirement. So it's that precise, right? 0.2%. That's about the average after 40 of decline of your brain. So happy birthday, 0.2%. yeah, you don't want to think about it. After 40, sorry. That's it's all it's about 20 seconds processing time. So the scan time you can choose, of course, depending on the resolution and the number of slices, etc. It's but we aim at about 4 or 5 minutes. It's about 20 seconds processing time. That is all on site, so you don't need any cloud solution or so, and we can set it up all automatically. So after the sequence, it can be directly parsed to our server. The server will do the post-processing and it will populate your packs. Right? Okay. Yeah. Well, of course, we wanted to make really sure that our current product, based on the MDME, provides exactly the same volumes as the KALAS sequence. This is part of what we send into the FDA as a performance data. So you can appreciate we get exactly the same results. It's actually interesting. Why would you go to 3D anyway? But for volumes, but it's very nice to do the reformat, of course. Next. So finally, the thing that is a bit more interesting, because 3D opens up a whole new realm for us, where we couldn't be with the thicker slices solution. I mean, even though the volumes are the same, we get now a much better grip on the irregular shapes and on the smaller structures that we want to go to. Yeah. First one out is we're working on a ventricle segmentation. So it's fully automatic. Today, we already have like synthetic images. We can find CSF in the entire brain. We do the ICV, but we can select now part of that CSF that is in the ventricles. So we have a number of neurosurgeons and neurologists that work with us to annotate what they consider to be a ventricle. And we have now it's a concept, but it's a 98% overlap with what they consider to be a ventricle. So it starts to be really stable. Yes.
It's like mortal with CSF.
This part you mean? Actually, there's a membrane over there. So this is exactly the mid slice, and so it's wrapping around that. So no, it's not missing. It's actually there, but it's on both sides. It just happened to be the fissure there. I guess you can see it here. It's a bit higher up in the brain that both parts are there. Don't worry. You don't worry. Let's go to the next. I think we have a very nice task here, especially for pediatrics, because the ventricle segmentation is really challenging in that area. This is an example from Cincinnati Children's, and so you can see that even if there are very irregular shapes or asymmetries, we can handle with that. That's a big difference with model-based parcellation. So there's quite a lot of companies around that do parcellation. They have a standard model that is then morphed to your particular patient, but it has its limits on how much you can morph. This is purely tissue-based. For every voxel, there's really a minimum of geometrical restrictions on that. So any shape would do. Highly irregular shapes would be fine. And well, this is what we envision, that it turns into some reporting system. You get a few slices that are displayed. Here it's actually part of it, but this is another slice. It's another patient too. You get the ventricle system also as a percentage of the ICV. Just for the fun of it, we do the Evans index, the frontal occipital ratio, and the colossal angle as well. And that's really interesting, actually. If you plot Evans index versus ventricle segmentation, then you definitely appreciate that Evans index is not so good to use. I've seen patients that have the same Evans index, but a factor 3 in volume difference of the ventricles, purely because of the shape. I don't think that's a good idea to pursue. So hopefully we can replace that with our automatic ventricle segmentation. Another thing is lesion detection. I mean, well, you can find spots in the brain on your flare, but it's very aspecific, right? It's everything lights up if it's out of the ordinary. And here, I think we truly have something to provide to the market, because we can actually characterize. So once we find all these spots, we can classify them too in where they are. This is an example that is already implemented in the software. It's actually based on this phenomena. It's kind of cool that it works. If you look at the R1 relaxation rate in the brain and the proton density, there seems to be a very intimate relationship between the two. And you get sort of all the data on one line if you plot the two. However, if you administer contrast media, of course your R1 will go up. So T1 gets shorter, R1 goes up, but PD, of course, is unchanged. So that means that all of a sudden your R1 is higher than expected. And so that means that if you consider this line as normal, that would be the pre-GAD brain. And if your data resides in the upper part, then all of a sudden that must be due to gadolinium. So we can automatically find it's actually proportional to the gadolinium concentration of this tumor. And now, of course, the tumor is pretty obvious here, but especially in these infiltrating areas where there's a very light enhancement, or if you reduce the dose, it's going to be super sensitive to use this kind of R1 mapping, and the very tiny enhancements that we can pick up. Mind you, a T1 weighted is a saturating image. I mean, it's saturated because of all the flip angles. So it's not that sensitive in the higher ends. This is purely linear. So any change in R1 is actually a change due to gadolinium. So I think this is going to be really interesting to find small enhancements, and maybe a method to reduce the dose of gadolinium. But there's more. I mean, if you choose not to use gadolinium at all, then, well, this is maybe a bit arbitrary, and we still want to communicate with different clinicians what we want with this. But this is the picture that we kind of see. Again, if we have R1 versus R2, we have the standard positions of CSF, gray matter, and white matter. So this is a normal white matter. If you find all the, what are spots on the flare, you can still put them in different areas. All these spots would be white. for flare. But we see differences, and kind of like a first suggestion, we think that here closer to the white matter are more the endemic lesions that don't show so much demyelination yet, but have edema. Therefore, they swell up and show up in the flare. If you have a demyelination, you would probably have traveled towards this part here with a lower R1 and a lower R2 simultaneously. It's kind of arbitrary where that cutoff is, of course, but here is really the myelin damage. And we also notice that if you administer gadolinium, you end up in the enhancing part. If you look at the pre-GAD images, they're always here. So if you're here, it doesn't say that you're enhancing, but if you're enhancing, you came from there. Right, so that's also a nice sign that this is in the separate area. Well, this is what we call liquefied, but it's kind of the black holes. So they are very close to CSF. They really burned out lesions. So we have the possibility to both classify them, of course, to count them, to get the volume, and really to follow this over time. And if you switch to the next, we think it's going to be very nice to have this as some sort of histogram. So we can plot volume or number, but then of the various classes. So a patient might have the same total volume of lesions, but if you shift in this histogram, there still may be something going on. So I think it's very important to have this characterization of lesions as part of it in R1, R2 PD. Oh, yeah, no. Oh, this is wrong. It's lesion, of course, but yeah, lesion. Yeah, all right. Yeah, just think we had it. Right.